Welcome to the 5th lecture on module 2 on the course on advanced marine structures under the brace of NPTEL IIT Madras. I am now continuing to discuss on the 5th lecture. In the last lectures in this module we understood what would be the disturbance caused in the fluid flow by interference of members. You place the cylinders in horizontal direction, vertical direction, along the flow, across the flow. There are vibrations induced or disturbances caused in the vicinity of the member, what we have understood as a wake region. We have also seen there are secondary vibrations set in because of the vortex induction or the vortex shedding frequencies, which can disturb and cause additional vibrations on the member and so on. We also see and understood that how these can be handled in the designer's perspective. Okay. We will continue to see them as one of the important application in this lecture to understand how the flow gets altered through a perforated cylinder. Presence of exterior porous cylinder reduces force on inner cylinder. This has been ascertained and verified by Wang and Wren. Whenever you have got an outer cover which is porous over an inner cover or inner cylinder which is solid, there is a force reduction on the inner cylinder. I am talking about reduction on the inner cylinder. Okay. This has been verified and quantified by Wang and Wren. There is also a significant reduction in the wave field and hydrodynamic forces experienced by the inner cylinder when it is surrounded by what we call semi porous cylinders. This application has been tested in breakwaters by Williams and Lee, and they have quantified that there is a reduction in the hydrodynamic forces on the inner cylinders when they are covered by semi porous outer layers in breakwaters. They have also seen that porosity, which is nothing but the ratio between the perforated area with that of the surface area which is non perforated, which is expressed as a ratio which we call as a porosity ratio. The porosity is one of the important parameter which significantly influence the reduction in hydrodynamic loads experienced by the inner cylinder, and of course it also alters the associated wave run up which is in the wake region of the cylinders, which has been also seen by Williams and Lee. It is shown that the wave run up and the run down ratio reduces with increase in porosity, but there is an upper limit for this. You cannot completely make the outer layer totally porous or totally pervious, then the effects get completely nullified. So there is an upper limit of this porosity which has been studied and examined by Vijayalakshmi et al. In 2007, and literature show that wave run up and run down ratio reduces with increase in porosity. Based on these, some studies have been initiated in the literature to carry out experimental investigations on an outer cover which is porous, which is covering an inner cylinder which is non porous or solid. So there are different studies or different experiments conducted. The inner cylinder diameter is kept as 110, whereas the outer cylinder is in different categories of 315 millimeter diameter, but different porosities varying from 6.3% to 16%. The thickness, perforation diameter, length of the cylinder and length of perforations are all explained in this table. So now we have got 3 cylinders, outer cover A, B, C configurations covering the inner cylinder with different perforation or porosity ratios. So the test specimens look like this. You can see here this is an outer cylinder A, B and C, and the inner cylinder is having no porosity or no pores. So these 3 outer layers of A, B and C have different regions of perforation which are covering the inner cylinder, and the forces are measured in the inner cylinder. You can see the instrumentation done on the inner cylinder. So the whole assembly now the outer covers of A, B and C on the inner cylinder separately are put in an assembly and they have been supported using a clamp, and the cylinder is suspended and the wave field is being activated. That is the setup what we have. Once we do this, the hydrodynamic forces on the inner cylinder, as I told you, are measured. The bending strain in the inner cylinder with and without covers are measured when the waves are passing the cylinders. Different regular waves have various wave heights varying from 5 centimeter to 25 centimeter, and wave periods varying from 1 to 2 seconds at an interval of 0.2 has been considered in the investigation. It has been seen that there is a force reduction. The table shows hydrodynamic forces measured in Newton on the inner cylinder for different outer cylinders of A, B, C for different wave periods. Of course, this table shows the value for a specific wave height of 25 centimeters. It is seen that there is a force reduction, and this force reduction decreases with increase in porosity. You can see here that when the porosity increases, the force reduction decreases. Further, the forces on inner cylinder decreases significantly for a short period wave compared to a long period wave. Okay, the reduction is significant for a short period wave compared to a long period wave. These two have been quantified experimentally to understand what is the effect of wave hydrodynamics on a perforated outer cover, and the effect is measured on the inner cylinder, which is covered by perforated layers of different ratio of perforations. So, ABC stands for different porosity ratios, as we saw in the last table. If you also look at the variation of wave forces on the inner cylinder because of the influence of perforations on the inner cylinder, the wave periods are selected appropriately so that the cylinder rise, of course, in the Morrison regime. The force variation seems to be non-linear. Okay, the force on the inner cylinders seems to be non-linear. So, the blue one is what you see here is the inner cylinder without any perforation. If you look at ICA, it is inner cylinder with perforation of outer cover A, B and C. You will see that the forces which are measured in inner cylinder reduces significantly for different perforated covers on the inner cylinder when they are having no cover. In both cases, one is for wave height of extreme 25 centimeter, other is for the other extreme of the lower value of 5 centimeter. In both cases you will see there is a force variation in the inner cylinder with the different outer covers, and this seems to be non-linear. You can also see that the decrease in the wave force is not proportional to the increase in time period and the wave height as well. Okay. So, this has been tabulated again, and the model has been studied at 1:140, is projected back in the upward scale to a prototype to find out what is approximate reduction in terms of meganewton on the prototype forces members when compared to the experimental values at different wave height, wave period. We have kept the wave period same in this table just to see what is the influence of wave height on the force reduction. So, from the table one can easily identify that the forces is significant in short period waves compared to long period waves. The reduction or the force variation is significant, and we have also seen that this variation is non-linear, as it is not proportional either to the increase in wave height or to the change in wave period. It is also understood that different layers of A, B, C configurations have been put on the inner cylinder. The size of perforation, because A, B, C has different size of perforation also, you can see that in this table. The perforation diameter for configurations A, B, C are not same, and the porosity ratio of A, B, C are not same, though the length of perforation is also varied, where the length of the cylinder is not varied. Okay. Therefore, we can now clearly say that the size of perforation and porosity influences hydrodynamic forces on the inner cylinder when it is encompassed by an outer cover. So, why this idea was studied? Because we have understood from the literature theoretically and analytically that, as we have seen from different references in the last lecture, that presence of porous outer covers will reduce the effects caused by vortex shedding frequencies on the members. We have also understood that there is going to be a force reduction on the inner members when outer cover is encompassed from different literature reviewed in this presentation very briefly. So, adding these two effects together, we have understood now that the size of perforation and porosity influences the aerodynamic forces on the inner cylinder significantly. The maximum force reduction is as high as 76% and as low as 17%. Therefore, one can make a very brief conclusion from this experimental study cited that the concept of force reduction on inner cylinder is emphasized. Further, the discussed example quantifies the value for different porosities and size of perforation, which can be understood as an important input for the design of marine structures with perforated members. One can ask a fundamental question: why the marine structural members should have perforated layers? We have seen in the last lecture that perforated covers or porous regions covering solid members reduces secondary responses caused by VAV. Primarily, they also reduce forces on the members. Now, is it a good practice to recommend this kind of application for a new structure? The answer is no. For a newly designed structures, reduction in forces may not be a good idea, though reduction in responses induced by VAV can be a good suggestion, but this kind of analogy is acceptable and recommended if you really wanted to strengthen the existing marine structures, what we call as retrofitting or rehabilitation of existing marine structures. Now, as an example of this application extended on a marine structure, a tension leg platform of members with outer perforated cover has been attempted experimentally and numerically. We all understand that TLPs are hybrid structures. They have very large surge, sway and yaw motions, which causes inconvenience to people on board, which we do not want. Therefore, to reduce the wave impact on pontoons and cylindrical members, one can think of attempting a perforated cover on an existing outer cylinder at highly stressed regions. This can be seen as one of the practical techniques to retrofit offshore coastal and offshore structures and also to improve their structural safety. Experimental studies are conducted on a scaled model of a tension leg platform using an 1:150 Froude scale model, which will be now discussed. This is the model of a TLP which shows an isometric view which is used in the experiments. This is the front view of the model. This is the description of the design parameters of the model, where the water depth studied of a TLP in the prototype is 450, whereas on a scale of 1:150 a 3 meter water depth is used for experimental investigation. The original material in the prototype is of course recommended as steel, which is used for a tension leg platform, but of course here the material used is acrylic. The mass ratio, which is one of the important parameter to influence VAV induced responses, is of course a limitation in this study. Okay, the mass ratio is now drastically different. This has been conducted only just to quantify the values to understand how this can remain effective, because you can see here the unit weight is about approximately about 5 to 6 times. Okay. Now, the outer cover can be of two different material which has been attempted in the study. One can be simply an aluminum cover, one can be an acrylic cover, two again has different densities. Now what would be the basis if you really wanted to conduct a study of this order? The basis could be the acrylic and aluminum covers can be used as exterior cylinders with porous members or porosities in the outer layer. In both the cases, mass of the perforated cover should remain comparable to the total weight of the model, but if you use aluminum, the added weight because of the cover is about 7% to the overall weight of the model, whereas if you use acrylic, then the weight cover comes to around 30%. Okay. Therefore, it is not a good practice to have a heavy density material as an outer cover in practice as well as in experiments, because one must match more or less the mass ratio between the material, at least between the inner and the outer cylinders, because it is essential that the comparison of dynamic response is possible only if the characteristics like mass and Cg of the model remains almost constant. So the model has been installed in a deep water pit in the experimental setup using the turnbuckle teether spring hook loaded system. Okay, the tension is given at the top. So this is the base plate which is having the arrangement to hold down the teethers in position. This is the steel base plate which is shown here. This is of course the same model which you saw in the last slide, which is now shown with the arrangement of accelerometers to measure the acceleration and inclinometer to measure the rotations. This is the arrangement of different measuring devices like load cell, accelerometers, inclinometers and wave probes, which are fixed or which is forming the part of the data acquisition system which is used in the experimental study. Now free vibration tests have been conducted to understand the response characteristics in the heave and surge degree of freedom. So if you look at the heave acceleration of the model with the perforated cover and the surge acceleration of the model with the perforated cover, as you see in the two figures on the left and right, the heave damped time period without perforated cover is around 0.17, whereas with perforated cover is 0.18, that is on the heave, whereas in surge damped period you will see that there is a significant variation in the periods with and without perforated outer covers. So damping is also affected significantly in the soft degree of freedom like surge. In the heave degree the variation is not significant for the model. So we have also understood that damping also plays a very important role, or one of the design techniques by which the secondary vibrations caused by vortex shedding frequencies can be controlled. Okay, because we spoke about external damping, we spoke about functionally graded materials where the damping can be increased by sandwiching materials like rubber or wood between the steel members to increase the internal damping, because internal damping characteristics when increased can control the responses because induced by vortex shedding frequencies. So in this case you can see here, by providing an outer cover to an inner cylinder we can achieve a good damping in a compliant degree like surge. Now the responses are now being discussed in a dimensionless format, which is steepness ratio of h by l. The TLP was subjected to a time period ranging from 0.8 to 2.4 seconds, because the model has a resonance close to 2.7. So the time periods of the waves were not taken to the resonating response on the natural frequency of the system, so that the model cannot be disturbed for a permanent damage. The wave heights tested were around 5, 6 and 7 and 9 centimeters in the course of the experiment. You will see that for increased h by l values, the blue line shows the responses on a 7 centimeter wave height in the model on a HC condition, that is 0 degree angle of inclination without perforated cover, but with perforated cover for a specific porosity value of 6.5%, you will see the reduction shows a similar trend but there is a reduction significantly for lower H by L values. Okay. For higher H by L values the reduction is not significant in the surge degree, whereas in heave degree, since the damping effect is not predominant, you will see that even at lower H by L value the effect is not significant. In case of pitch, of course the effect is significant and the trend remains same, and the maximum reduction occurs at a specific value of H by L which is developed or which is seen as a coupling effect between the heave and pitch degree of freedom. Interestingly, you will also see that the tether tension variations, that is the tension variation in tethers or cables, are also significant. For higher H by L values the reduction is significant. So, perforated cover or perforation layers on an inner cylinder encompassing the inner cylinder not only decrease the response of the members in inner cylinder, but also decreases the tether tension variation. I am not talking about the tether tension reduction, the variation is controlled significantly. Therefore, this can also be seen as one of the ideas of indirectly controlling the vibration induced responses on cables, which is also one of the ideas on VAV reduction phenomena which we discussed in the last lecture. If you look at this trend for different angle of attack at 45 degree, for example, for a 7 centimeter wave height the same wave height is being kept for the same range of wave period and wave heights, you will see that the trend is again similar, whereas in pitch and tether tension radiation you will see that the variation suddenly has a significant effect even at a specific H by L value close to around 2 or 1.8, then the trend follows. As you see, the increase in H by L causes significant reduction in the tether tension variation as well. So, this can be seen as one of the ideas of retrofitting the members which can also reduce the tether tension variation in the cables or in the tethers. If you look at the surge responses in oblique waves for 30 and 45 degrees, the percentage reduction which you see in the 4th and the 7th columns as you see in this table is significant, varying from 15% or let us say the lower percent is around 7 and the highest reduction is around 27%, which is significant for a model of 1:150 scale which has been discussed in this presentation. If you look at the heave responses in oblique waves for a 30 degree and 45 degree, the variation or the reduction in the variation percentage reduction varies from about 6% to as high as 17% for 30 degree as well as 45 degree. It means the angle of attack or angle of approach of the waves on the member encompassed by perforated cover does not cause significant variation, because whatever may be the angle of attack, the percentage reduction remains almost same, varies from 6% to around 17% in this case as well. So, it is understood that there is a significant percentage reduction in surge and heave responses on the inner members when they are covered by perforated outer covers. There is a reduction in tether tension variation when you cover the members using perforated outer cover. We have understood that there is a reduction in the response which can be connected to increase in damping coefficient in surge response, because the moment you put an outer perforated cover, the damping coefficient in surge degree also varies significantly. If you look at tether tension variation for oblique waves, the percentage reduction for 30 and 45 degrees is also varying from as normal as no variation, that is 1%, to as high as 33%. Okay. So, there is a reduction significantly in tether tension variation as well. If you look at the average surge response reduction, you will see that for increase in wave periods from let us say 0.6 to 2.4 seconds, you will see notice that there is a significant reduction in percentage which happens at around 1.2 let us say in this case. Then afterwards the percentage reduction changes drastically. So, you can also see from the table here the average reduction is varying from 13.35 and drops down to 7%. So, there is a critical value of wave period in the experiment conducted at which the reduction is lowest, but once you skip this region then the reduction becomes as high as 25%. The presented example highlights the advantages of deploying perforated column members on an example problem of a TLP as an outer cover on an impermeable inner layer. It can be seen as one of the direct application of force reduction on inner cylinders, though the application is not desired for a new design, but recommended as an alternative method for retrofitting of marine structures. So, we can see that the wave forces increases in the inner cylinder with increase in porosity, decreases in the inner cylinder with decrease in perforation size, reduces in the inner cylinder significantly by the presence of perforated outer cylinder for a short period waves compared to long period waves. Force percentage reduction increases with increase in wave height. So, perforated cylinder reduces wave forces, which can be seen as one of the direct method of retrofitting marine structures. Subsequently, this has been also verified using numerical studies. The numerical studies on perforated cylinders are carried out using a software simulation in STAR CCM. The idea was to simulate the hydrodynamic response with a porosity of 6.3%. Software CCM is chosen because the numerical capabilities enabled in different modules to simulate viscous drag and turbulent effects are good in this software. The numerical model of a perforated cylinder is developed in CATIA V5 as shown in the figure here. The pocket tool perforations are created along the circumference and the length of outer cylinder using circular pattern and rectangular pattern tools respectively. The details of cylinder created in the model numerically are shown here. In the outer cylinder A, for a different diameter, you can see the length of the perforation is kept as same as the experiment of 1450 millimeters and the porosity is achieved as 6.3% numerically. This picture shows you the inner cylinder with the outer perforated cover generated in STAR CCM for numerical analysis. Let us quickly see some of the details of the numerical model. The center of the inner cylinder is kept as an origin with its bottom surface and xy plane. The length of the domain block is taken in such a manner to reduce the reverse flow effects in the simulation. The width of the block is taken equivalent to the width of the flume. The height of the domain is taken equal to the characteristic length of the inner cylinder that is effective during the wave structure interaction, because the domain has got to be defined very clearly in the numerical model. A surface and subsequently a volume mesh has been generated using the meshing tools in STAR CCM. This is defined by the base size, while the trimmer model is used to generate the volume mesh in the model. The efficiency of the generated model is relatively high because it is capable of producing high quality grids that consist hexahedral cells mostly. The prism layer meshing model is used along with the trimmer model to improve the accuracy of the flow solution. The present numerical simulation, the mesh parameters are set globally and altered at specific boundaries as desired. The volumetric controllers are assigned to generate the desired mesh after assigning the appropriate regions and other required parameters. If we look at the reference values of the mesh size used in inner cylinder and inner cylinder with perforated cover, you can see the base size of the mesh in this case 100 mm, whereas in this case 200 mm, and the absolute prism layer thickness is 7 mm in the inner cylinder, whereas when you use PC it is taken as only 2 mm. The number of prism layers in both the cases is kept as 2, and the surface size is not varied much, whereas the base size is varied significantly from 25 to 100, that is what the limit is, whereas in this case 250 to 200, that is what the limit is. This is how the model looks like for a domain of inner cylinder and the domain of an inner cylinder with perforated outer cover. This is a domain what we are showing here. Different boundary conditions deployed for the analysis for the inner cylinder is basically inlet, outlet, walls and of course the cylinder, whereas for perforated outer cover we have got 5 boundaries: inlet, outlet, wall, inner cylinder and perforated outer cylinder vicinity of the model as a finer grid. Implicit unsteady model is chosen under the time group in star CCM. Under the chosen approach, each physical time step involves number of iterations to converge to the desired solution. The volume of fluid VOF model is used to simulate the behavior of the two fluid, that is air and water. As two fluids are of different phases, the Eulerian multiphase model is used in the present simulation. The flow is retained as turbulent. Turbulent option is chosen in the viscous regime group in the star CCM. Turbulence effects are simulated by selecting the K epsilon turbulence in the Reynolds average turbulence group, which is most widely used in similar numerical models as see from the literature. The effect of gravity is simulated using the gravity model, while simulation of waves is made possible under the option of VOF waves. The new Eulerian phases are created and defined. Water is defined as constant density fluid and air as an ideal gas. The segregated fluid isothermal option is used for the energy group. Motion of the structure is selected as a stationary for both the simulations. Total of 16 physics models are used in the present simulation and then activated subsequently. The first order wave is created under the wave's child node of VOF models. The point of water level is set as 0.54 meter for inner cylinder and 0.8825 meter for the inner cylinder with perforated outer cover. The chosen values are matching with the relevant values used in the experimental studies, as I showed you in the table in the last slide. The wave amplitude for the experiment for the numerical study is set as 0.05 meters. The specification type used is wave period, and the numerical simulations are run for 6 waves of each model, wave periods varying from 1 to 2 seconds at an interval of 0.2 seconds. The changes are made for the settings under the volume fraction, velocity and pressure nodes. The volume fraction is set to composite, and the method of each phases water and air, they are set to fluid function. The boundaries in the region are set to match various types of boundary conditions. Inlet boundary is set at velocity inlet, outlet boundary is set as a pressure outlet, and inner cylinder and outer perforated cylinder are set as wall boundaries. The velocity specification method in the velocity inlet is changed to components, and the velocity and volume fraction values are set identical to that of the experiments. The volume fraction and pressure settings of the pressure outlet are also set accordingly in the numerical study. The time set property of the implicit unsteady solver is set to 0.01 seconds. Under the stopping criteria, the maximum inner iterations property is set to 10 and the maximum physical time is set to 10 seconds. The initialized solution tool is selected to activate the required simulation. An ISO surface with an ISO value of 0.5 and the scalar set to volume fraction greater than water is used to visualize the free surface. Now after doing all these settings, you can see the screen set from star CCM for simulation of inner cylinder in the boundary and the simulation of inner cylinder with the outer perforated cover in the boundary, both generated in the star CCM software. If you look at the residuals which are arrived from the numerical simulation, which is used as one of the check measure to see whether the results have converged, the inner cylinder and inner cylinder with perforated cover are subjected to unidirectional wave. Wave periods are varied. Reynolds average Navier-Stokes equation is used and is solved, used for converging with the residuals which decrease by multiple orders before setting around 0.001 001 as you see in this figure. The results and discussions as you see here for force and inner cylinder in numerical simulation and force and inner cylinder with perforated outer cover in the numerical simulation for the same wave period and wave height. If you compare the results and look at the error varies, the force inner cylinder varies about 13% as high as that, whereas in case of forces on inner cylinder with perforated cover varies as high as 11% for different wave periods, and you will see that how are they compared with the numerical value obtained from the star CCM with that of the experimental value measured in the test setup in the laboratory. And the error what it shows here is the comparison between these two. So it is as high as 13% in the inner cylinder without outer cover on the forces, whereas with outer cover on the forces as high as about 11% again. If you compare the results on forces on inner cylinder with and without cover, you will see that these are showing inner cylinder experimentally, these are showing inner cylinder analytically. So they match very closely for higher wave periods. And if you look at the results with inner cylinder with perforated cover experimentally, the triangles and the crosses, you will see that even for lower periods the force measured experimentally and the force computed with inner cylinder with perforated cover, which is the idea of the whole experiment, is matching very closely with a very less error of only about 7 to 10%. There are some few problems associated with the simulation which I want to tell to the viewers before they attempt such a similar study in their research. High cell numbers are required to simulate this kind of studies, which is one of the important restriction or limitation in the study. Large domain attempted to simulate the condition as that of the wave flume. This resulted in not yielding the velocity profile variation, because the interesting thing could be whether can we examine the velocity profile variation also. What we saw in the literature now or in the study now is only the force variation. If you want to really look at the velocity potential variation also, then the larger domain attempted in the study is not suitable, okay, because it requires more desired points along the cylinder if you really want to trace the velocity profile variation. This can be seen as few limitations in the numerical study which we have experienced when we compared it with the experimental studies. This particular presentation has references from different authors as you see here. So different studies are also being quoted by different researchers in various regimes of comparing experimental and numerical studies. You can also see the porous effect parameter on thin permeable plates as studied by Lee et al. In 2006. As we have also seen some of the studies conducted in our own laboratory by different researchers at different time periods. As you see here, people have attempted to study the aerodynamic response on twin perforated cylindrical systems experimentally and analytically. So the studies referred, emphasize, and the case studies mentioned show that there is significant reduction in the forces on inner cylinders encompassed by porous outer cylinders. Literature also verified, as we discussed in the last presentation, that they also reduce secondary vibrations caused by VIVs. So this can be seen as one of the interesting application area of force reduction or retrofitting members on marine structures. Thank you very much. This leaves and completes the discussion on the module 2, where we discussed very briefly about the flow induced vibrations, variation in flow characteristics because of interference of members in the steady and uniform flow field. We have also seen some of the thumb rules suggested by the designers, some of the empirical relationships recommended by the codes by which you can handle the lift force coefficients which are caused because of secondary vibrations induced by the vortex shedding frequencies on the near vicinity region of the members. We have also shown you two interesting case studies, experimental and numerical, where force reduction has been quantified and showed numerically and compared experimentally on scaled models. So, these discussions in module 2 definitely leaves a very important aspect of designer's perspective of understanding how the flow induced vibrations and how the flow past cylinders helps one to understand what would be those parameters which should be considered while designing marine structures, which is seen as one of the interesting and recent advancements in marine structures. Thank you very much.